Okay, so it asks us to determine with the equations and with a ray diagram. You can use one to check the other, okay? I'll do the ray diagrams on paper so you can see them here. I'll do the math on the board. So let's start with a ray diagram for this one. So a 5 centimeter tall object, okay, 5 centimeter tall object, so that's H object, is 30 centimeters to the left of a convex lens. So that's D. Oh, the object is real, of course, so it's going to be positive, okay? To the convex lens with a focal length of 10 centimeters. So convex, so this is a converging lens, so that focal length is positive. Okay, but we're not even worried about that yet because we're just doing the ray diagram. Principal axis, principal plane, drawing the lens, measure out the focal points on both sides. Okay, so it's 30 centimeters to the left of the convex lens with a focal length of 10 centimeters. So whoops. Again, you don't have to be super careful. What is important to do here is to make sure it's beyond 2 focal lengths. I'll go ahead and be a perfectionist and kind of make it actually be 3 focal lengths because that's what 30 centimeters is. But again, all you need is for it to be beyond twice the focal length for it to work out okay. Okay, so there's my object. Let's go ahead and do our rules. So ray 1 is parallel to the principal axis, and then refracts at the principal plane through the focal point. Okay, I'm going to do the center one first because that's the easiest one, honestly. You only actually need 2. Okay, so through the center, unrefracted. And look at that. We can already predict that we should be getting an image here. What kind of image is this? Real, right? Real, because these are real rays of light. They're not dotted. Those actually are converging. Okay, real rays of light. This is going to be a real image. Let's go ahead and check, though, with our third rule, which is that through the secondary focus, it will go parallel. So through the secondary focus, hits the principal plane, and goes parallel. Look at that. Beauty. So good. If I'm checking my work, that's a very, very good feeling that they all meet there. Okay, so this is a real image. So type of image, real. Orientation / attitude, inverted. Okay. Size of image, we don't know the actual number, but we can tell that it's definitely diminished. Smaller, in other words. Okay. Location, we don't know the actual number, but it's on other side of lens. That's how we knew it was real. Well, we knew it was real because real rays were converging, but that helps us know for sure, right? Way of thinking about it. And it's between the focal length. So at the focal length is less than di, which is less than 2 times the focal length. So we can really check the numbers with our math. I'll go ahead and do that now on the board. Okay, so let's check that now with our formulas, see how it turns out for us. So again, a 5 centimeter tall object, so that's height of the object, HO, is 30 centimeters to the left of a convex lens, so that's distance the object. Okay, that'll be positive because of course the object is real, with a focal length of 10 centimeters. So this is a converging lens. Its focal length really is converging light, right? It's a real focal point. It's really focusing parallel rays. So that's a positive focal point, okay? Focal length, I should say. To determine with the equations, the location of the image. So let's start there. So 1 over the focal length is equal to 1 over DO plus 1 over DI. If we want to know where the image is, we need DI, obviously. So just manipulating this. That DI is equal to the inverse of 1 over the focal point minus 1 over object distance. Don't forget that's all inverted. So 1 over all of that. Okay, so DI then equals 1 over positive 10 centimeters, because this is a converging lens, minus 1 over 30 centimeters, all inverted. Okay, just because there will be physics courses in your future where you can't use a calculator, let's just think about how we could calculate this without our use of our calculator, okay? So 1 over 10 minus 1 over 30. To subtract those, we need a common denominator. So we could do, well, 1 over 10, we can multiply this thing by 3 over 3, right? And get 3 over 30 centimeters. We're allowed to do that because multiplying by 3 over 3 doesn't change the number, right? That 3 over 3 is just 1. What it does let us do, though, is write it in a way where now we have a common denominator, right? 3 over 30 is the same as 1 over 10, but now we can do this. So DI equals 3 minus 1 is 2 over 30 centimeters, right? Then we can flip that, power of negative 1, and there we go. Without a calculator, we've now solved this. So DI equals 15 centimeters. Just a good skill maybe sometimes to try out is, can you solve it without a calculator? There will definitely be math courses and probably physics courses in your post-secondary where you will not be allowed a calculator. So it is good to work those muscles as well. Okay, but DI equals positive 15 centimeters. There we go. Positive, right away we know it's real, okay? So it's real. And for a lens, that means it's on the other side of the lens as opposed to the object, right? It's on the opposite side of the lens as the object. Really what it means though is that real rays are converging, right? Which is what we saw in our diagram. Good, real rays, not dotted virtual ones, not projections, are actually converging. 15 centimeters on opposite side to the object. Okay, so what about the size of the object? Well, for that, we can hop over to this guy. M equals negative DI over DO, okay, which equals HI over HO. We could find the magnification. The question didn't ask for that, but we totally could here. However, since it doesn't ask, let's just go straight into this guy, because all it wanted was the size, which just means HI, right? So multiplying both sides by HO, get that HI is equal to negative DIHO over. And let's go ahead and plug in. By the way, you could really quickly here just kind of probably pull out the magnification. Negative DI over DO is magnification. So we have negative 15 over 30. The magnification will be negative 0.5. So this thing should look half as tall, but inverted, right? So we're going to get that HI is negative 2.5 cm. And sure enough, yes, that tells us it's inverted and diminished, right? It's smaller than it should be. What did our ray diagram tell us? Real, diminished, inverted. What did our math tell us? Real, inverted, diminished. Perfect. Okay. Size, negative 2.5 cm. Obviously, that's diminished. Okay. Type of image, real. Orientation, inverted, just like our ray diagram said. Okay. Let's do the ray diagram for this one. So describe the characteristics of the image produced when the object is between 1 and 2 focal lengths away from a converging lens. Between 1 and 2 focal lengths away from a converging lens. Okay, so this is one that actually lends itself pretty well to a ray diagram because they didn't give us numbers to work with. However, as I'll show you after the ray diagram, you can still use math on this one. Okay, math will still work. You just got to pick some numbers. So set up our ray diagram. Principal axis, principal plane, draw in our lens, measure out the focal lengths. Okay, so the object is between 1 and 2 focal lengths away from a converging lens. So let's put it right smack dab in the middle, right? Between 1 focal length and 2 focal lengths. Remember, yes, this is the focal point. What is the focal length? This, right? This is F, which makes this 2F. Okay, don't forget the difference between the focal point and the focal length. Focal length is just the distance to the focal point. All right, so let's put our object right smack dab in the middle. And we'll do our first one. Parallel hits the principal plane. And then through the primary or the principal focus. Okay, next one. Through the middle, no refraction. Well, no overall refraction. Of course, refraction does still occur. Okay, so boom, already I can say looks like it's going to be real, inverted, and beyond 2 focal lengths. But let's double check. So something that a ray that goes through the secondary focal point will get refracted parallel. Okay, and just like that, sure enough, looks like we have our image here. Okay, so checks out. What are the properties of this image? Well, it looks farther away than the object, right? Farther, because it's beyond 2F. Whoops. Beyond 2F, whereas the object was between 1 and 2F. This thing's beyond 2 times the focal length. Is it upright or inverted? Definitely inverted, upside down. Okay, larger or smaller? Boom, boom, way bigger. And real or virtual? Well, what kind of light rays are producing this? Are those real rays of light that actually left from the object actually are meeting? Or are they mere rays of light that are just appearing to meet, but don't actually exist where they meet. Right, those are real rays of light. They just got bent to meet over there. So this is real. Okay, let's now use the math to check our ray diagram here. Of course, you could go the other way too. In fact, I'll do that for the next one. Okay, but you can always use your ray diagram to check your math as well. Realistically, the equations are probably going to be mostly what you work with, just because a ray diagram can be kind of time consuming, but still an important skill. Okay, so I told you that we could still do math with this one, right? And we can. Just because we're not given actual numbers doesn't mean we can't, because the characteristics of the image depend on where the object is relative to the vertex, the focal length, and twice the focal length, right? So we can just say, pick a number that we can just kind of pick a spot and make it work. So if we are between 1 and 2 focal lengths, how about we let between 1 and 2, how about 1.5, right? Let DO equal 3 over 2 times the focal length, 1.5 of the focal lengths. That's between 1 and 2, right? 1 over the focal length equals 1 over DO plus 1 over DI. But DO is 3 over 2 focal lengths, so we'll sub that in. Okay, just going to, I'm dividing by 3 over 2, so that's the same as multiplying by 2 over 3. So 2 over 3 F, right? Don't put that F up top, right? That's still in the denominator. Now just solve for DI. So 1 over F minus 2 over 3F equals 1 over DI. Okay, again, we need a common denominator here. Here we really need to use it because there's no numbers at all, right? So you can't just rely on your calculator. You have to be able to do this. So I can't do just 1 minus 2 because, well, these aren't the same denominator, right? 1 over F minus 2 over 3F. I'd first have to get a common denominator. So I could multiply this by 3 over 3, right? And then I would have 3 over 3F. I haven't changed the number. I've just changed how it's expressed, right? 3 over 3F is still 1 over F because those 3's could cancel. Minus 2 over 3F, 1 over DI. Okay, and there we go. Now I have a common denominator. So 3 minus 2 is 1 over 3F equals 1 over DI. If 1 over 3F equals 1 over DI, I could think of it as just flipping both sides, or truthfully, that just means those things are equal, right? If 1 over this equals 1 over this, then this must be equal. So that would give us then that DI equals 3F. So the image distance is 3 times the focal length. So 3 times the focal length. And what was DO? Well, DO was 1.5 focal length. So if DI is 3 focal lengths, it's twice as big as DO. We can also just see that by subbing DO back in, right? If DO equals 3 over 2F, then F equals 2/3 DO, right? Just dividing both sides by 3 over 2. So then 3 times 2/3 DO, that's what F is, gives you 6 over 3 DO, gives you 2 DO. So DI equals 2 DO. Okay, so what does that tell us? Well, obviously DI is farther, right? Farther, because it's twice as far from the lens. Its DO is positive by default pretty much, right? So if DI is equal to 2 DO, not negative 2 DO, then DI must be positive and therefore real, okay, on the opposite side of the lens as the object. So real and farther, that's what that tells us. Confirming what we saw, right? We imagined it to be farther and real from our ray diagram. Now for upright and inverted and larger and smaller, we're going to need to go to heights and magnifications. So let's keep this going. M equals negative DI over DO. Okay, so the magnification is going to be equal to negative. We said DI was going to be 3F, and we said DO was going to be 3/2 of F, right? 1.5 Fs. So look what happens here. Focal lengths, those cancel. You can think of this as 3 divided by 3 over 2. Dividing by a fraction is the same as multiplying by the reciprocal. So we could think of this as equals 3 times 2 over 3, right? Dividing by a fraction, the same as multiplying by a reciprocal. And what do you know? The magnification equals 2x. That's the magnification, okay? Whoops, I dropped a negative, right? The negative was there, negative, negative. So the magnification is negative 2x. You're multiplying its height by negative 2. Well, the negative means you're making it upside down, right? You're flipping it. So it's inverted, and negative 2, you're making it twice as big, just upside down, so larger. What did our ray diagram say? Real, enlarged, inverted, and farther. Perfect. That's exactly what we got, right? So enlarged, inverted. Okay, now I'm going to do this one with the math first and then check it with the ray diagram just to mix things up. I know the ray diagram's already there. That's just because I did it before. Okay, so let's go ahead and do the math first, and then we'll look at array diagram and see how we can use that to confirm. Okay, so again, this is one where we have to make some substitutions. The object is beyond twice the focal length of a converging lens. Okay, so pick a number. Let's say 3f. That's beyond the focal length. Okay, so let DO equal 3 times the, sorry, that's beyond twice the focal length. So let DO be 3f. Okay, then that equation becomes this. So DO becomes 3f, right? Get here. And then again, need a common denominator. So 1 over f is the same as 3 over 3f, right? That's the same number, just written differently, written in a way that allows me to deal with it here. So 3 minus 1 is 2 over 3f equals 1. And give both sides a flip. So di equals 3 over 2f, right? Okay, so what does that tell us? Well, remember, do was 3f, which is twice of 3 over 2f, right? 1.5f, or even just 3 over 2, twice of that is 3, okay? So it's definitely closer. We can also just show that. 3 over 2 times what was f? F is, how can we show that? Well, do equals 3f, so f equals do over 3, right? So if we go plug that relationship in, do over 3, just putting that in for f, boom, and we get that. Yes, definitely now we've shown that di is smaller than do because di is half of do. Di equals do over 2, right? So what does that tell us? Closer, right? It appears closer. The image distance is smaller than the object distance. And this is also positive too, right? There's no negative anywhere in there. So closer and real. We'll check that on our picture. I know you can kind of see it there, but to figure out the other stuff, let's look at the magnification. So magnification equals negative di over do, which equals negative di was, we found it to be 3 over 2 times the focal length divided by do, which we said was going to be 3 times the focal length. Again, guys, we're just making these numbers up because, hey, that's beyond twice the focal length. So that works. Whatever our results tell us will work. Okay, these are not the actual answers or anything, but they can tell you the information you need. Okay, focal lengths cancel, f over f. We have 3 over 2 over 3, which is the same as dividing by 3 is the same as multiplying by 1/3. So that's negative 3 over 6. And that is the same as negative 1/2 x or negative 0.5 x. Okay, so it's getting multiplied by a half, right? That's going to make it smaller, and not just any half, negative a half. So it's going to flip it. It's going to make it inverted. Okay, we can check that now with our ray diagram. We'll actually draw it out. All right, so we got our math for this one saying it should be closer, real, smaller, and inverted. Let's now check that with a ray diagram. Principal axis, principal plane, lens, measure out the focal points. Okay, and we're looking when the object is beyond twice the focal length of a converging lens. So it's beyond twice the focal length. So let's just put it here. Why not? Okay, now rule number 1, any ray parallel will pass through the focus. That's the whole point of the focus, right? Through the principal focus. It focuses parallel rays no matter where they come from. So, yoink. Okay, rule number 2. Well, it's actually rule number 3 in your notes, but I say use this one second probably. Okay, through the center with no refraction. So looking like the image is going to form there. Let's double check with probably the trickiest of the rules. Okay, remember folks, you have the advantage here of knowing what these lenses do. So you know that a converging lens is going to bring rays together. If it doesn't look like your ray diagram's doing that, maybe rethink what you're doing on one of them, right? So if I had done something wonky there and got that it bent away, I would say that's not what a converging lens does, right? And rethink it and go, oh, whoops, okay. All right, so yep, definitely confirmed. Okay, there is an image there. Okay, just like our math said, that is a real image. It's appearing closer than our object, right? It's within 2 focal lengths, whereas here it was beyond 2 focal lengths. So closer. It appears inverted. Check. That's what we got with our math. Okay, and it appears diminished or smaller. So that all checks out. Okay, so that wraps up the examples for topic 1. Now you can definitely go try the practice problems that go with topic 1. Look in the agenda or on the Google Classroom for those.